morning, and I'm from Beihang University in China. My name is Yongmei Zheng, and today I talk about bioinspired multi-gradient surface materials for water collection and repellency. As well known, smart wettability is very important and in many applications, for example, cell adhesion and microfluidics and biological medicine, and also molecule manipulation and dual delivery and safeguard system, and also dual and water collection and filtration and microfluidics and anti-fouling and anti-ice and ice phobic and so many applications. And for example, challenge in the fog water engineer, for example, and the water collection is in the low efficiency, and the problem is our challenge is how to design smart water collection materials and how to use nanostructure effect and enhance water collection and efficiency. And also, another example is we are also suffering from icing and ice adhesion on the surface. So the problem is how to resolve the strong ice pinning on the surface and how to remove the ice, and also. So the scientific issue is, for example, interface effect on the liquid controlling, and also cooperation effect between the micro nanostructures, and how to small size effect on the liquid driving, and how to control the switch off and on wettability. And also how to design a gradient inclusion as geometry and chemistry, roughness and curvature for the moment of the droplet, and also tuning three-phase interface for the control the wettability. And as well know, a smart wettability in the nature, for example, many biological surface display a strong wettability and to be controlled. For example, the safe word amounts are for the delivery, transportation, and the street legal and street move faster on the water surface. So the street legal for the superhydrophobic force, and also street spider silk for the water collections, and the lost leaf and for the superhydrophobic. Also, and the string and for the water aquarium and beetle bag, and also for the water collections and butterflies, similar lot leaf, and for the water collection and self-cleaning, and so many. And those smart wettability is attributed to the micro nanostructure on the surface. Those surface has a character of the multi-gradient. I think multi-gradient. And the multi-gradient, coupled to multi-gradient and control the wettability. For example, the gradient, for example, is on the street leg and with a gradient, for example, a curvature roughness. And the beetle bag has a white bulb difference on the surface. And also butterflies and lost leaf and has a different gradient, for example, ratchet and anisotropic and the geometry, and so many gradients on the surface. So an idea is to get in learning from the biological surface and to design the surface with a micro nanostructure similar to biological. And for the to design and new materials and for the applications, for example, collect water and fire reaching and so many applications. What we do is to fabricate bioinspired surface to control water collection and repellency. This our publication and with culture stories in recent years. And the first work we are involved direction water collection on the whited spider silk. This work with cover story and highlighted by many medias. And this work is we revolved spider silk has a spider silk and changed micro nanostructure in the medias. So droplet condenses on the spider silk and droplet can be moved direction. And so droplet larger and a larger on the spider silk. So spider silk display a strong water collection and also efficiency. And we wrote this method is attributed to white rebuilt multi-structure. This structure is like this, and white spider silk is after whited is change the structure and is composed of the spindle node and the joint. And the spindle node and the joint has a different curvature gradients, and on the spindle node and on the joint has a different structure. This different structure has generates a different roughness in gradient. So the droplet condensation on the whited spider silk droplet can be controlled by the composition of the surface energy gradient and the Laplace present. A surface energy gradient is introduced with a gradient, roughness gradient reduced by the roughness gradient, and the Laplace is result from the curvature gradient. So droplet can be moved direction, droplet can be driven by the composition of the both gradients. So the next issue is how to design the gradients and how to fabricate and to control control the surface with a gradient, and how to drive the tiny droplet directionally, how to modulate the application of the water collection. And we developed fabricate, for example, we use reliability, instability law, and to combine the traditional method, for example, deep coating and electrodynamic and the fluid coating and microfluidic. So we use this the reliabilities, and we all know the reliability and enable the elevator coating film and break after the pure rate droplet. The pure rate droplet can be controlled by the polymer contrition, and also fluid coating, fluid while sheeting, and also think of the film. So this pure rate droplet is similar to the spider node, whited spider node. So we use this method and fabricate different size structure fiber with a spider node. We call this spider node, and similar to whited spider silk. And we found the different size spider node can be controlled and different pH, and on the spider node has a different gradient. So we use this method and fabricate different size spider node, similar spider silk. And for the we are designed. We use the method and we design a different functional spindle node and on the fibers. So we, for example, and we investigate and the droplet can be driver, tiny water droplet can be driver, and also droplet can be transportation, and also we developed the white assembly method and also we are handling larger droplet and so many functions. And so next we introduce my work and in details, and for investigation different size we use the different size spandrel node and for the water collections, and we found spandrel node, a larger spandrel node has a strong water collections, and we are investigation the method is in mechanism is the uniform fiber, and spandrel node fiber has a different handling drop. We found, and spandrel node has a larger droplet. It's attributed to different three-phase contact length. And we issued observation the droplet can be pinning by the spandrel node. So droplet can be handling drop, and spandrel node fiber display strong water collections. And also we investigation the spandrel node. We control the spandrel node fabricated, for example, roughness spandrel node and smooth spandrel node, and droplet can be more direction. And also we fabricate a smooth spandrel node and uniform parallel spandrel gradient parallels, and we found gradient parallels has a strong water collection. Droplet easily can be moved on the center of the spandrel node. And also we found the number of the spandrel node is very important for the water collections like this, and much spandrel node has on the fiber, so the fiber handling a larger job. And we also fabricate heterostructure of fibers. Heterostructure fiber has a different hydrophilic, hydrophobic. For example, bead is hydrophilic, and string between the bead and is hydrophobic. So droplet can be easily collect water in the bead, and display respond humidity in the environment. And also we fabricate the nanofibers. The nanofiber is in place the fog, and the fog in the nanoparticle. So the particle easily, the fiber easily absorb the nanoparticle, and after the water condensation, droplet are formed on the fibers. And after dry on the spandrel node and stay on the fiber. And these fibers and has a spandrel node and similar to spandrel thick, and this fiber and display are strong water collections. And furthermore, we fabricate, we use this method and fabricate and spandrel node, and we use the titanic and particle and the titanic particle and gadget on the fibers. After we control the water collection and control the whiting, and so the fiber can be easily formed spandrel node. Spandrel node easily formed on the fibers. And also we use the response of the polymer and solution to coating and to fabricate the response of the fibers. And especially spandrel node and response to the, for example, temperature and photo and photo. And so droplet on the surface, on the spandrel node and on the surface, so droplet can be controlled by the temperature and the photo. So tiny water droplet can be controlled. And also we fabricate and gradients. A gradient has a different size and on the fiber. So droplet easily move to the larger size spinal node. Its attribute to the largest spinal node has a strong adhesion, and so droplet can be moved direction and target on the larger size. And also we control the velocity and coating, and different mode spinal node can be formed on the fibers. For example, on unidirection gradient and middle and the center center asymmetry and two-side asymmetry, and the different mode gradient can be fabricated. So droplet can be target controlled position and larger, and the droplet can be moved. And the electric fiber also can be fabricated. Droplet can be collector, and droplet can be relaxation. So we also so we use the fiber can be controlled collection and controlled droplet falling down and droplet relation. And another surface can be controlled. We use the, for example, this surface similar to spiral beetle bike, and for example, and hydrophilic and hydrophobic, we fabricate a white ball pattern, a different white ball pattern surface. For example, the circle and target-shaped white ball patterns. So droplet collection has a difference. And we found the target-shaped white ball patterns display strong water collection. It's attributed to the target-shaped has a gradient. The gradient pattern in the white ball patterns. And for the water repellency, we fabricate another structures. The structure is, for example, the micro-nanostructure are oriented microstructure, and also anisotropic anisotropic and structure. As well known, butterfly display strong water repellency, and also droplet easily rolling directionally, and also the this surface and also display strong and water repellency in the low temperature, and also for the condensing droplet and the water butterflies also are repelled. Also repelled condensing droplet. And for the grass leaf, and also on the surface also are oriented gradient, so droplet easily rolling off. And the loud leaf also are suspend up, and the tiny water droplet. And also the some structure is attributed to the gradient on the surface. And so we fabricate a different structure surface, for example, micro-nano structures and smooth structure and nano structures and micro-nano structures. And we investigate the water repellency and also isotropic on the surface. At the on the surface at the low temperature, and we found micro-nano structures, and if droplet on the micro-nano structures and droplet has a long delay time to frozen. So the micro-nano structures display strong water repellency on the low temperature below the zero. And this surface, micro-nano structure surface has a low adhesion for the eyes. And for another work, we fabricate an oriented nanofiber on the surface. Oriented fiber and make the droplet has a difference of viability. For example, and we revolved if the droplet and if the surface is hydrophilic, usually droplets are separate and has a contact angle of the 0. But if the hydrophilic surface at the surface with oriented higher, and the droplet easily roll direction as the surface has a high temperature. For example, 350 temperature, and the droplet on the hydrophilic surface droplet also easily moving direction. It's attributed to the oriented structure, and in the structure has oriented ice pocket and driving the droplet. And the gradient also can be fabricated micro nanostructures. For example, the Piro has a gradient, a nano gradient. So droplet can be display direction, and the droplet is in the different temperature. Droplet easily rolling direction. It's attributed to the gradient on the surface. And another work is the higher adhesion surface. High adhesion surface. And if the gradient on the high adhesion surface, and the droplet also move direction, also sprint direction. And the gradient can be direction, unit direction, and center asymmetry, and two-side symmetry. And so droplet can be move and direction, and can guide in the center, and separate more to the two sides, and so many. And also we fabricate and radio writable surface. So droplet also can be controlled. The droplet can be moved, and we control and move the center and move the side. And also we control the droplet and the target on the surface. It's attributed to the gradient on the surface. And recently we fabricate and magnetic the wall, micro wall, and droplet on the surface, and the wall can be controlled and move, and so droplet can be moved direction by the magnetic control. So that's all we wanted to conclusion. And we all know the surface has a full mode. For example, smooth surface, and micro nanostructure surface, and nanostructure surface, and micro and nanostructures. And the different surface structure has a different viability. For example, smooth and microstructure surface droplet on the surface are easily pinning, and the surface has a high adhesion. And for the nanostructure surface and micro nanostructure surface, and droplet on the surface, and droplet is easily in the case stage, and droplet is low. And this surface has a low adhesion, and this surface has also has a water collection and water repellency and low temperature. And this surface is easily and ice-phobic to be controlled. And for the droplet motion, Droplet motion, I think the droplet can be controlled by the gradient. So the surface must be can fabricate and gradient. For example, structure gradient, and geometry gradient, and roughness gradient, and also a chemistry gradient, and also so the droplet can be controlled by the cooperation gradient. For example, the cooperation force is composed of the chemistry force and roughness force and curvature force and multi-gradient control the droplet. So droplet easily can be roll, can be spread, and can be moved direction. For the future, and we want to fabricate and many structure and many function structure, and for the multi-functions and for applications. Some work is going on. And this work is, acknowledged is, the work is how supported by the funding, many fundings, and across many groups and students and teachers, and so many. And that's all. Thank you for your attention.
Thank you very much, Professor Zheng. Questions? Yes?
Since I'm not familiar with this kind of work, but looks like fascinating to me. So I'm curious about when you fabricate this, let me say, fiber and a different, like a
different spindle.
Yeah, different those
yeah.
tiny things.
Yeah.
How do you do that? How?
And we fabricate. Usually we coating, and this for example, and horizon and velocity, and gradient, and we have a dunate coating.
Okay, so
Dunate coating and has a different thickness polymer on the surface, and rarely instability and broke up on the surface, and different thickness and different broke up different size and polymer droplet.
okay.
After dry and droplet on the surface form the spindle node at different size.
Okay.
Yeah.
So this apparently, okay, you have to do one spot at a time. Apparently, it's a slow process. Do you think this can be, let me say, automated? Let me say, if I wanted to use this kind of, or if I want to make this kind of material for, let me say, industrial application, you have to manufacture in large scale and continuously in order to, economically feasible. And I'm curious about, do you think that can you envision some relatively fast approach down the road? Do you think it's possible to do this kind of thing?
You mean the fabrication?
Yeah, fabrication. Can you think right now looks like if I understand correctly, so you do it one at a time, another at another time for different size,
Yeah.
and also different surface properties.
We use the fluid coating and
Fluid?
yes, and a long time and like this. We are yes. Fluid coating and has a long time and a larger size. Like this. Like this, the moon and fluid coating.
Oh, okay.
Yeah, fluid
Okay,
coating.
I can ask you.
And yeah, we collect the fiber and the larger size.
Okay.
Yes.
Okay. Any further questions? If not, let's thank Professor Zheng once again.